Hydroboration-Oxidation is an alkene addition reaction where we are essentially adding the elements of water, namely an H on one side and an OH on the other side, to an alkene or a carbon-carbon pi bond. It's an addition reaction because we're adding in new elements to a molecule without removing any existing elements. And this one is essentially the anti-Markovnikov equivalent of hydration. Hydration also adds a hydrogen to one side and an OH or alcohol group to the other carbon in the alkene. However, we add the OH to the less substituted carbon, which makes it anti-Markovnikov. This reaction also has a stereochemistry, in particular it's syn-addition. The hydrogen and the OH that are added simultaneously, effectively. And so that means that they are added, in this case, to the same side of the original alkene, so they're syn to each other. Now that, we won't necessarily see that stereochemistry in an alkene that's not in a ring because of free rotation of the alkane bond afterwards. But if our alkene is a double bond in a ring, then we'll see that stereochemistry. We'll look at a quick example. We won't go through the entire mechanism in this case, but we'll look at the addition step because that's the one that's most important in that it tells us why we get both the stereospecificity and the regiospecificity. Quick note on reagents. This is a two-step process. First step is a borane reagent. Could be B2H6, could be BH3, could be BH3.THF. It could be anything that has boron and hydrogens present. Well, not anything, but anything that you are likely to see in a two-step process where the first step is boron and hydrogen containing reagent and the second step is peroxide and aqueous base is going to be one of these reactions. There's a good variety of different reagents here at the top in the first step, so I want you to be aware of that. This is specifically a two-step process because if we dump them in all at once, we're going to get a big goopy mess and the reaction won't work. So you need to have the one and the two present, otherwise you are not emphasizing that you have to put the first one in, let time pass, let it do its thing, and then add the second set of reagents. And let's look at an example like 1-methylcyclohexene, where we have a double bond in a ring, and the alkene is asymmetric, meaning that there are two different groups, one bigger than the other, located on that alkene bond. And what happens is that the borane, and we're just going to draw the hydrogen and the boron so that we don't have to have it be too complicated. The borane will approach the alkene, could be from the back, could be from the front, but from one side or the other of the alkene, and then it will align itself such that the hydrogen from the borane, which is relatively small, and the larger rest of the molecule align themselves to complement the existing groups, which is to say the smaller hydrogen is going to be where the bigger group on the alkene is, and the borane connected to several other things is going to, which is a larger group, is going to line up with the smaller group of the alkene in order to minimize steric interactions. What we have next then is called a hydride transfer, which is essentially fancy talk for this hydrogen taking its pair of electrons, moving to make a carbon hydrogen bond, and then the pi bond simultaneously breaking, reaching out and connecting to the boron. That will give us, after this step, we've added the hydrogen to one carbon, to the more substituted carbon. And let's just say that we added that hydrogen to the front. Could have added front or back, but we got to pick one. And we'll push the methyl group out of the way accordingly. We'll do the same thing on this carbon. Doesn't matter if it's front or back, as long as it's the same side as the hydrogen. the borane approach from one side or the other. Both of these things happen simultaneously, and so we're conserving or keeping those two groups in the same location. Now the B, of course, is not the OH, but the subsequent step, so this is what happens in the first step. The second step, where we're using water and peroxide and base, over the course of a couple of steps, this boron is replaced with the alcohol group. Now we won't bother going through how that happens. That mechanism, of course, is available to you from other sources, but again, not one that I'm holding you responsible for in this class. And so we just are comfortable saying, well, the OH will take the place of the boron, and even keeping its relative position, or its position relative to the hydrogen that was also added. So in this case, we have a reaction that's anti-Markovnikov. The OH ended up on the less substituted carbon, whereas the hydrogen ended up on the more substituted carbon where there's fewer H's for it to hang out with. And it is stereospecific, it's syn-addition. The hydrogen and the OH end up cis to each other. Now note that this can be a little bit confusing, because if we were simply to write the skeleton structure of this product, we have actually created trans 2-methyl-1-cyclohexanol, because the original group and the alcohol are trans to each other. But the original group was not added during the reaction. What was added was the hydrogen, and the hydrogen, which isn't shown here, is actually cis to the OH group that was added with during the reaction.